Benjamin Delaware, or Ben Delaware. I'm an assistant professor at Purdue. Before that, I was at MIT. I did a postdoc with Adam Chapala, who will be here next week, or later this week, actually. And this project actually started out as an undergraduate project working with Swit here, and has since grown into a bit larger project. And so I'd just like to begin by describing where I think this fits into the larger context of deep spec. Well, you notice that on the slides that were the overview that was presented yesterday afternoon, that there was no Narcissus, piece of Narcissus. So I want to explain where I think this fits into the big picture and how it can be inspiring to you, maybe, for where you will fit into the big picture someday. So I probably don't need to recap this, but just to set the stage, there have been numerous developments of high assurance software systems and proof assistance in the past 5 years. CompCert-C, the CompCert-C compiler, Sotacross, FSCQ, SEL4, several examples at this point. Indeed, many of the examples that were mentioned yesterday, right? And of course, the reason that we refer to these artifacts, these systems, as being high assurance is that their assurance comes or is somehow conferred from the formal guarantees that are provided by a proof assistant. Of course, in our case, in the case of deep spec, Coq, but in SEL4, it's Isabelle Hull. And so what's the story here? So typically, we have some implementation, we have some specification, and we write some proofs, right, that Coq will check for us, saying that the implementation meets the specification, right? And we're happy and good, and it's completely correct, right? Well, mostly correct. So there's a little asterisk right here. What does the asterisk stand for? And this was, of course, alluded to yesterday, that whenever we talk about a particular development, formal development, being correct, it's always with respect to some trusted code base. And I think that may or may not have been mentioned explicitly before, but I'm going to call it out right now. And so in any of these formal developments, there's always some piece of code that you're trusting, right? So typically, we always trust the specifications. We can test the specifications, but it's very hard to verify the specifications because they themselves would need a specification, which is quite difficult. And of course, we typically trust the proof assistant, the proof checker of Coq, which is safe most of the time, right? And then, of course, once you have this implementation, depending on, well, the state of the art previously was we had some compiler, and we would extract it to a binary and link it against some other components, some libraries, the operating system hardware, right? And typically, these would be trusted. And before CompCert-C, this compiler would also be trusted. If you're going to use Coq's extraction mechanism, it will be part of your trusted code base, of course, right? And the sort of nasty little truth about all of these things is if you get something wrong and something you trust, well, everything sort of falls apart, right? And part of the motivation behind deep spec, and I think really the promise of deep spec, is that we're shrinking what we have to trust to a very minimal code base, right? We're eliminating the operating system with Sotacross, the compiler is going away with CompCert-C, the hardware is being alleviated by Kami, so we're really building an ecosystem where we can operate in with maximal trust and build high assurance software, right? And part of living in this ecosystem is that it can grow, and we can contribute new components to this ecosystem to build better pieces of software, right? And so where I see Narcissus is as part of this entire ecosystem of high assurance software. It's a component, a piece of it that's being developed and will hopefully become part of it and can leverage these existing developments, and they can leverage this component, and Coq will make sure that everything plays together nicely. And maybe, here's the inspirational part for you, hopefully someday you too will be using this ecosystem, leveraging this ecosystem, and contributing vital components to this ecosystem. Was there a hand? Oh, okay, sorry. It's a little early for questions, but I should note that just as, I think we did a good job this morning, if you have any questions, feel free to raise your hand, and this will be more interactive that way, hopefully. Okay, right, so today's talk is about one such component. So what is the component in particular that we're going to be building with Narcissus? So here's a really important part of every piece of software that has to interact with a network or some external format, is the code that's responsible for taking some piece of data from the outside world, typically supplied in some standardized, agreed upon format, and transforming it, deserializing it, I'll say here, into some source or target data that your program can understand and manipulate. right? So if you think about a DNS server, you get these DNS packets in some binary format that was standardized in the 1990s, early 1990s, I think, and you have to decode that and understand in order to process the query and make a response. So of course, if the code that is responsible for deserializing stuff from the untrusted network is buggy, you're going to break your assurance case, right? Oops. And in fact, I mean, your entire proof of trust sort of falls apart. And in fact, there was a paper at ESOP, I think last year, showing that there were some formally verified distributed systems that had admitted their code responsible for handling packets as part of their trusted code base, and those pieces of code were wrong, and it was able to, the authors were able to break the guarantees, the assurance case that was provided by the authors of those papers, right? So Narcissus is all about removing this code, this deserialization code from the trusted code base, right? So what is Narcissus? If I had to summarize it, enter Narcissus. So Narcissus is a user extensible framework in Coq for deriving semi-automatically encoders and decoders from format specifications with machine-checked correctness proofs. And I will get into precise detail about what all this means, but you can imagine now we've gone from having to trust this piece of handwritten code or generated code that's responsible for handling this deserialization to looking at some specification that captures the sort of data you anticipate getting. You take that as input, and you get as output, hopefully automatically, two pairs of functions, a serializer, we'll call it, and a deserializer, that are guaranteed to be inverses of each other. Or you could think of them as being inverses of each other in a way we'll spell out concretely, shortly. No questions so far, I hope. OK, so that's today's talk in a nutshell. So I'm going to be talking about Narcissus, which is, again, a system for deriving these correct by construction functions in Coq as encoders and decoders. But what I also hope to communicate to you is a bigger idea about the power of Coq as a system for building programs automatically. And what do I mean by that? Well, everyone in this room, or at this point, having been to the Coq Intensive, if you didn't know Coq before, is familiar with Coq as a system for writing down programs by hand. We write our functional programs, we write our verified C, and then we prove things about it. And sometimes that's manual, but we can actually use tactics for verifying things automatically. And today I'm going to try and convince you that we can leverage the same machinery that we use to write proofs automatically to automatically generate programs or software that is correct by construction. So we'll actually make it not only easier to write proofs with these tactics, we'll also make it easier to build correct software using tactics. And I will use this particular domain of encoders and decoders as a motivating example. OK, so in order to do that, I'm going to give a quick, well, not that quick, an overview of Narcissus. I'm going to show how we can embed formats that have been standardized for many, many years in Coq as a sort of specification. I'll discuss how we can actually interpret these formats as specifications for functions for translating to and from some piece of source, for translating a piece of source data to and from these target encodings. And I will also discuss how we can automate this whole process using tactics in Coq. And then hopefully after this, you will be inspired to go write your own automatic code synthesis engine inside a proof of system. So to begin with, in order to sort of motivate Narcissus, I'm going to try and provide some examples of how you might do this right now. And so we're going to walk through a couple of examples before we dive into more of the nitty-gritty details. So let's just consider the following extremely simple binary format, the sort you might see written in some request for comment document, right? So here's what we get from our user perspective. So over here, we have some source data type that we're actually writing down in Coq. We're going to find a simple record. It's just going to be a pair of products or a product of products representing some simple record. So we're going to have a word. You can just think of this as being a fit width bit string. We're going to have some user-defined data type. And then we're going to have a vector of bit strings, or words, that will represent the payload of this packet. And then over here on this other side, we're going to have some specification that's going to be written in ASCII art, because that's the way to do these things, specifying how to lay out these values on the wire in terms of a bit level representation. So here, if we look at this, we can see that this identifier is probably an 8-bit word because it needs to fit in 8 bits. This timestamp is going to be somehow encodable in 16 bits, and then this payload is going to be variable length. But note that this is a vector, so at some level, this specification has a fixed number of bytes that's going to be included in its payload. Okay. So how might we go about writing an encoder and decoder function from this? Well, you know, it's a little bit tedious and error prone, but I think everyone here could maybe come together, write some function that, you know, takes a source data type and transforms it into a bit string. And you can imagine you have some components for, you know, helping you do this. So we could imagine we might have a couple of functions that explain how to encode particular data types and put them on the wire. So here we're going to have a function for formatting words on the wire, and we're going to have a pair thing that's going to take 2 formats as argument. It's going to show how to format the left-hand side and the right-hand side, and from that you can build up a format for the pair. Yes, Andrew?
Why is there no n argument to vector format?
It's vector format. It's probably a typo. Okay. Yes. This is
magic or implicit.
If only it were magic or implicit. No, this is transcribed from LaTeX, which is known for being a ill-typed or weakly typed language, I'm afraid. Yes, and ditto, you can imagine that this word actually has an implicit argument specifying how many bits are supposed to be there that I've elided for clarity of presentation. Okay, so we wrote this function, and you know, because we might be writing a lot of these encoder functions, we can build up this sort of selection of functions for composing these formats, these encoder functions together to build up bigger ones, right? And we can imagine playing a similar game for decoders, right? We could have a similar library of decoders for base types and for composing together sub-decoders to build up larger ones, like so. And we might write this down by hand, and you can imagine sitting down at the terminal and writing a lemma showing that these things are inverses of each other in a proper sense. And I will just note for now, for this intro, I'm going to leave a couple of things undefined for your intuition. So you can imagine decode M here can be interpreted as a function from target to source as a first approximation. And similarly, a format can be interpreted as a function from a source type, in this case our simple products, to some target type. Okay, great. So you look at this, and you'll naturally think to yourself, well, this is sort of silly. These things are so tightly coupled together. It's very clear there's a strict correspondence between each of the components we use to define both the format and the decoder. Why not just package these together as sort of a library in the style of parser combinators like you might see in Haskell. So the idea there, of course, is you have packaged together these encoder and decoder functions, and you can build up sort of both the encoder, decoder in a compositional way. And in Haskell, you sort of say, oh, of course, they're going to be correct, and we'll reason about them independently, and their composition will thus be correct. The nice thing, of course, about Coq is that we can package together proofs alongside these functions, right? So here we're going to have I'm going to call it a combinator, which for all purposes, we can just think of being a package of one of these formats, one of these decoders, and then it also is going to have this rather nice proof component, witnessing the fact that these functions are in fact inverses of each other in some way that, again, I will spell out precisely in a little bit. Okay, and so any decoder or correct decoder, we can think of it as just being an inhabitant of this type, right? Because we have this proof component, as long as we can build up an inhabitant of this type, you know, for any source and target type, well, then we know that it's correct. It's correct by construction, by definition. And what's great about having defined inhabitants of types? Well, Coq, as everyone knows, is quite good at finding inhabitants of types, right? This is precisely what we do with tactics when we're writing proofs. And so, in theory, we should be able to automate this process of finding correct encoders and decoders as a search for a member of one of these types. And in fact, this is not a new idea. This is a rather old idea, this idea of using a proof assistant to build certified software in this sort of interactive manner. And in fact, this is a term. It's called deductive synthesis. You might have heard of program synthesis in other settings. Well, there are many flavors of synthesis. You might have heard of inductive synthesis, where people give examples as specifications of programs, and the synthesizer tries to infer a function that meets those examples. You might have heard of sketched or template-based synthesis, where people write down partial programs, and they use the theorem prover to synthesize an implementation. Well, in deductive synthesis, we're going to write down a complete full functional specification, and then we're going to use the theorem prover to find an implementation of that specification. And I think the term, well, if it wasn't first coined by Richard Waldinger, it was, he certainly mentioned it in 1981, which was before I was born, so we'll label that as being as one of the first mentions of this term, deductive synthesis. Okay, so this is fine and great, but if all we have are this definition of records, it's not very helpful because we haven't really solved anything, right? If we have to manually provide an encoder, a format, and a decoder, and then write down the proof for every particular format, this hasn't really bought us anything. Well, the observation of these combinator libraries in Haskell is that they're quite compositional, and you can take together little components and glue them together to build up bigger components. And it turns out that, at least for this simple example here, that the proof-carrying combinators are actually quite compositional in the following sense. In much the same way we define this pair format function, high-order function that took together two formats and built up a bigger one, and a decoder, high-order decoder function that took together two decoders and built up a bigger one, we can actually define a proof-carrying combinator that's going to take together two provably correct components and glue them together in a provably correct way, once and for all. And so this will allow us to take together smaller components that have been verified in Coq and glue them together to get a complete verified compiler. And you can imagine, with some extra combinators for these base types, it's fairly straightforward to interactively define a correct decoder and format encoder and decoder for our simple record type. Okay, we're just going to apply the constructors of each of these combinators. We'll decompose it into finding a decoder for the left-hand side and the right-hand side, and just work our way down. And in fact, this is so straightforward and easy, we could even imagine just using Auto with a hint database to automatically resolve these things. Yes?
Could you slide and explain the word defined instead of QED?
So why did I say defined here? Well, the important thing is when we finish defining a term interactively in Coq, we have two choices. We could say QED, which says, you've written this definition, and now I'm going to make it opaque. And when it's opaque, you are no longer able to peek inside the definition. And this is good for proofs. However, if you're trying to actually extract the functions we defined interactively here, you want it to be transparent. So you can actually pull the functions out and say, execute them. And so that's why I use defined here. This says, take the term you've built up and attach it to this identifier, and also make it so that I can unfold that definition later. If we said QED here, they wouldn't be very useful functions, I'm afraid. Any other questions? Yes? Yes?
Okay, so are list combinators necessarily bijective?
In full generality, the answer is no, and we'll get into...
Repeat the question.
Oh, sorry, right. I will repeat the question for posterity. The question was, in their full generality, the question was, are these combinators necessarily bijective? And the answer to that is, in their full generality, no. And we'll spell out exactly why in a little bit. Yes. But you could, yeah. We'll see why in just a few seconds. That's okay. Okay, so okay, this is great. We're done. We sort of checked all the boxes I